Hello, and welcome to the next session of my webinar on standard C++ template library by example. Today, we'll be turning our attention to yet another type of ordered associative container, the map, as well as its sibling, the multimap. We'll talk about how to use the maps and walk through some very interesting examples that demonstrate their structure and their functionality. So let's go ahead first and take a look at where we can find the code, and then we'll jump right into the analysis. Start by sharing my screen. You can see here that the code is going to be available in my C++ STL S-05 repository at my GitHub account, and we'll be focusing on the examples in 5.5, 5.6, and 5.7. So let's pop over to my CLion interactive development environment. As you may recall, a map is an ordered associative container that associates key objects with value objects. And it's called a pair associative container because its value type is actually implemented as a pair of const, key, and value types. Keep in mind, of course, as with the set, that the key is const. We can't change it while we're iterating over it because that would cause chaos and insanity with respect to the ordering, which under the hood is implemented using a red-black tree, which is an ordered binary tree that's balanced. For a map, the key must be unique, just like with a set. The keys don't have to be integers, so you can basically have it be an associative array or associative data structure where the keys can be any types. Keys can be strings, keys can be anything that has a way to be able to search using the less than operator. Here are the various parameters that are passed to the map template. Of course, you have to pass the key, like a set. Unlike a set, though, you can pass a value, or you must pass a value, which is the type that's associated with the key. You also have to pass a comparator operation, or you could just let it go and use the default, which is the less functor. And then last but not least, you also can pass an allocator optionally. But by default, of course, it'll use the standard new and delete free store operations from the global heap. So the key characteristics of a map is if you insert a new element into a map, it doesn't invalidate the iterators that are already pointing to existing elements. That's because it's implemented as a tree, just like set. And erasing an element from a map also does not invalidate any iterators except for the ones that you happen to be pointing to that you're erasing. Of course, those will be affected. If you want to use a map, you have to supply the key type and the data type as the value. And you can also choose to provide the comparator function if you want. In the examples that we'll be using here, we'll be using the default less operation. But of course, you can always choose to use your own operation if you want to sort it in a different order. Much like we did with set, where you could pass in greater as opposed to less. So here's our example, and this is a really cool example. So if you take a look here, you can see that we're going to give it a vector of strings that we're going to manipulate, and it's going to be the famous phrase, "Now is the time for all good people to come to the aid of their party." And what we're going to do here is we're going to type def a map to be a string to int mapping. So what we're going to do here essentially is we're going to keep track of the number of times each word shows up in our input. Then we go ahead and we make ourselves a word map, which is just this string to int mapping. And we then go ahead and we iterate through the word list using a range-based for loop. I'll show you some other ways to do this in a second, but I want to focus on the range-based for loop because it's very concise and clean. So you can see here that we go through for every word in the word list, and we treat this as an auto const ref, so there's no extra copying going on. And then we take each word and we index into the word map with the word as the key, and then we increment the count, which is the value, which is the int. And due to the magic of C++ initializers, all the values in the map, all the ints will all start out with the value 0, which is good, so we don't have to initialize them ourselves. So look how cool this is. We're just going through there, indexing into the map, almost as if it's an array. It kind of looks like what's called an associative array. And we're indexing by string, and then we're incrementing the count by 1. So we're basically keeping track of the number of times each word occurs. Just for kicks, we could use some other ways to do this. We could use this with an explicit iterator using the format shown here. It's a little verbose. We could also use an implicit iterator, do much the same kind of thing with the auto keyword. But I think for my money, I really prefer the range-based for loop because it's just so much more concise, and it lets the the compiler deduce the types for you automatically. So once we've got ourselves the map, what we're going to do is we're going to go ahead and print out the word maps. We're going to print out the count, in other words, the number of times each word appeared, followed by the word. So that's what's going on here. Again, we use the auto const ref to avoid making any unnecessary copies, and we print things out. Now we're going to have a little bit more fun with some other C++ features. We're going to show functors first, and then we're going to show lambda functions second. So we're going to create a functor, which is called total it. And what it's going to do is it's going to keep a count. And as you can see here, this count will be initialized when we pass this in. We'll give it a 0. And then every time the operator function call method is called, and we'll see how this gets called in just a second, it's going to go ahead and increment the internal I underscore count by the second parameter. And the second parameter here in this pair, which is the value type for the map, is going to be the count of the number of times each string was located. So that's going to go ahead and zip down through there and do all the counts. Here is the actual code. We are going to have a running total we call total, which is an auto. Of course, it's an int. And then we're going to use the for each algorithm. And the for each algorithm is an interesting STL algorithm. We'll look at it in a second. What it does, as you can see here, is it goes through a range from beginning to end in an iterator range. And it's going to go ahead and pass an anonymous copy, anonymous instance of total IT, given the initial value of 0. And what for each is going to do, as we're going to see, is it's going to go ahead and call the operator function call method for each element in this range. And let's go ahead and take a look at what for each looks like. You can see, as usual, it's a very straightforward algorithm. Most of the STL algorithms are very straightforward, but they're so cool because of the use of adapters and other magic to make them work in all kinds of interesting ways. So as you can see here, we have the for each algorithm. It's parameterized by an input iterator and a functor or a function or a function object, probably a better way to put it. And so what we're going to do here is we're going to go ahead and take the first input iterator and then the last input iterator and the functor, and we walk through the range from beginning to end, and every step along the way, we call the functor on the current value we're looking at with our input iterator. So under the hood, of course, what's happening here is we're passing in the total it object by value, so it gets copied, and then it goes ahead and calls the functor, which is the function call operation on that particular total it object. And so what you can see it's doing, it's just totaling things up. When we're all done, the for each method returns the functor that we've been manipulating. So we get, by value, we get a copy back of that. And that is used here in a clever way. So we go ahead and we get back an object of type total it, which we call it. And then we go ahead and we're going to store the value here into this total variable. So now it's going to be a count of the number of times, or the count of the number of words that were found in the input. So that's one way to do things. Now let's go ahead and take a look at another way to do things. So let's face it, creating this functor that really just is doing this. I mean, this is the secret sauce of that functor. Wouldn't it be nice if we could just focus on the logic of the function and leave away all the other syntactic sugar to make it be a structure, a class, and whatnot? And the answer is yes, you can do that. And this is the magic of C++ lambda functions, which are similar to Java lambda expressions, although the syntax is ever so different. So what we're going to do down here is we're going to re-implement this using the for each algorithm with a lambda function this time. And you can see that we go from beginning to end in the word map. And each time through, we're going to write a little piece of code that's going to get called each time. And what it's going to do is it's going to take in the const word map value type ref, which is going to be this pair. Remember, the value type of a map is a pair because it's a pair associative container. And we take this in by reference, so there's no extra copies made. We grab the second field, and then we update the running total. And you'll notice that total is passed in here with this interesting little syntax. This is called a capture clause. And what we're saying here is we're saying pass total by reference so that we can update its value. And then when this functor is done, this total here will actually have the total, the running total that we compute. If we get rid of this capture clause, then we can't be updating it. So it becomes a read-only object. So let's go ahead and run the code here. This is a neat example. You can see here that what we get is the output, which is in this case ordered, because it's an ordered tree that's implementing the map. And so it keeps track of the number of times each of the words appear. Most words appear just once, but the and to appear twice. And you can see that that's printed out here nicely. And then we go ahead and total up the total number of words that we had using both the technique, using the lambda function, as well as using the functor. And naturally, we get the same results. So I think this is a really, really cool example. It demonstrates just how concise C++ STL is and the maps that they use. And I just, for some reason, am in love with this particular piece of code. It's just so to the essence of what's going on. Okay, so that was the first example that I wanted to look at. Let's go ahead and take a look at another example. This should be 5.5b. So let's go open that guy up, and we'll take a look at it. So this is going to illustrate a few other features of STL maps. Keep in mind, again, STL maps cannot have duplicates. We'll talk about multimap shortly that can have duplicates. So here we have a print functor. And again, we could have used a function, a lambda expression. I think we actually do at one point. But here's just the simple functor version. And as you can see, it's a struct because it's really stateless. It doesn't have any state associated with it. We don't want to hide anything. I'm not trying to hide the fields, for example. And so as you can see, it's going to take a value type of a map, which is a string-to-string mapping in this particular case. And it's going to print the first part of the pair for the value type, and then the second part as well. Okay, so let's just take a look at a few examples. This is real simple. We make a pair we call 7 heaven and print those results out. That's really kind of simple and mindless. We then do something else kind of fun. We go ahead and we create ourselves a pair that's been allocated dynamically, and this is going to be the whole 9 yards. And this particular pair is going to be allocated dynamically, and then we stash it into a unique pointer so that it will be released automatically when the scope of the unique pointer goes away. So that's just demonstrating how you can combine these pairs with pointers if you want to, but you're always well advised whenever you start using pointers in C++ to never use raw pointers, or what I like to call naked pointers, but instead encapsulate them in the context of the holder class, in this case, unique pointer. All right, so that's just some interesting stuff. Now let's go ahead and make a string-to-string, basically English to German dictionary. And I'm only going to put a few words in here just to make it interesting. So we're going to basically create the dictionary that starts at empty, and then we're going to use the subscript operator to assign the shun value to the shu key and the kof value to the head key, because kof is head in German and shun is shu. I'm probably pronouncing that wrong. And then down here, just for kicks, just to show you yet another way you can do things, we make ourselves a value type, which is, of course, a pair. And we're going to say that the German word for yes is ja. And then we insert this value type into the dictionary. So this is a way we can do things where we're inserting with the subscript operator, putting the value associated with the key. And then over here, we're inserting a value type, which is a pair, in one fell swoop. And you'll see that for maps, you can do it either way. For multi-maps, you have to go with the insert for various reasons. So now that we've got ourselves an initialized map, let's go ahead and print it. So we go ahead and print from beginning to end of the map using the print functor. That's one way to do it. And we saw the print functor was defined up here. And then the next thing we're going to do is we're going to go find the word yes, which is the key. We're going to get back an iterator to that, which we treat as an auto, just to keep things nice and concise. And then we can go ahead and erase that key using the iterator. We also could have erased it just by erasing yes, but this way we show you can use find to find the appropriate location, and then we can erase that location. And I probably should have been smarter to not try to erase it. I probably should have said something like if iter equal engr dict end, or maybe I should say not equal. So in other words, we actually found it, then we can go ahead and erase it, because we don't want to be erasing something if we didn't find it. And then the last thing we do here, just for kicks, is we go ahead and iterate over the map that's now no longer got the yes, ya value type in it. and we print the results, and this time we're going to use a lambda function. And this is probably a good use of lambda function because we're just trying to have the very essence of the computation, which in this case is going to be printing out the first and the second, as we did up here with the print functor, but it's a little bit less ceremony in some way. You don't have to litter your code with all these extra structs that are lying around, or classes, functor classes that are lying around. And down here you can see that we use the functor syntax, the lambda syntax, and we're not passing any parameters here that we need to update. This is all purely going through cout. I suppose I could have said, I could have passed in cout and not had to directly address it in this scope, but I think this is fine and nothing, we're not writing to it or anything like that. Okay, so that's the next example. I think that's kind of cool. We show a few other features of map that's worth being aware of, like you can insert value types, or you can do the subscript operation to give it the key and then do the value as an assignment from that. And we saw yet another example of how to use lambda functions. Let's now go ahead and turn our attention to the next example. And this is 5.6a, and this is going to be fun. So we've talked about maps up to this point. Now we're going to start talking about multi-maps. So as with sets, a set only has unique keys, whereas a multi-set can have duplicate keys. And it would be no surprise, it would be the principle of least surprise if multi-maps work the same way with respect to map. So a map can have only unique keys, but a multi-map can have duplicate keys. Of course, a multi-map is also an ordered associative container. It's a pair associative container, as we talked about before. The only real difference is you can have duplicate keys, but everything else is the same. So the signature in terms of providing the key type and the value type and the compare type and optionally the allocator. And if you don't give compare, it defaults to less. All that stuff works the same. Okay, so this particular example is a really fun one, and it's going to show off a whole bunch of cool stuff. So let's take a look. As you can see, we're going to make a few type defs. We're going to define names type to be a multi-map that maps string to string. And we're going to define value type to be the value type trait in names type. And that's just to kind of keep things a little bit less verbose. And you'll see why we need that later when we do the bulk of the code. We also define a helper functor that will go ahead and, as we've been doing, print things out to the right location. In this case, rather than just defaulting to cout, we're going to pass the output stream we want to write to as a parameter to the constructor, and then it stashes it away internally in the base member initialization section. And that's what then gets used down here with the actual operator function call. So hopefully that is intuitive to you, not unlike before. And notice how we're passing in a value type, which is a pair, and so we can print the first and the second of that. We also have a couple of insertion operators that are kind of fun. And here's the first one up here, right here, is going to take an OStream ref, and it's going to take that OStream ref, and it's going to go ahead also and take a names type. So names type in this case is going to be basically the multi-map, and it's going to go ahead and go through the names type from beginning to end, because after all, that's a multi-map, so it goes through the whole range. And it's going to use that print functor we saw above to print each element in that map to the standard out, using whatever's passed in here, not the standard out, to the OStream that's passed in, which turns out to be standard out. But it could be something else. So this is the for each algorithm. We've already seen the for each algorithm. Just a quick recap. Here's for each. It just goes through that range and invokes the function on every single element. And the function in this case is a functor. Okay, so far so good. So that basically prints out the contents of a multi-map to whatever OStream you give it. Then down here, we do something similar. In this particular case, we're going to go ahead and we're going to print out a pair. So rather, before, as you saw, what we had was the ability to print out a whole multi-map. This time, we're just going to focus on printing out a pair. And you can see you give it a pair, which is a pair of iterators. And so in this case, we're going to use the for each algorithm to go from the beginning of the pair to the end of the pair, not including the end of the pair. So the range between beginning and end, or first and second. And again, we're going to go ahead and print the contents out to whatever OStream is passed in. And these are just convenience methods you'll see in a second that make the rest of the code really concise and to the point. All right, so now we're ready to talk about the code that's concise and to the point. And as you can see here, we've got ourselves a main function that declares a names type object called names. This is the multimap. So we have a multimap of names. And then we're going to go ahead and do some interesting things. We're going to first start out by inserting value types containing people's first names and last names. So we're going to put the first name in as the key and the last name in as the value. And we kind of have to use value type when we do insertions for multimap. And that's because of the fact that you can have multiple keys with the same name. And so this just makes sure that it all works cleanly. There is no subscript operator defined on multimap like there is for map. So we're going to go ahead and insert Kim, Jane, and Kay Smith. And then for some kicks, we're going to show a little optimization. So we use names. Oh, so when you do insert, that of course starts at the root of the red-black tree and then goes and does binary search through the tree till it finds where the location of the item goes. It puts it in there, and then it rebalances the tree to make sure it stays balanced. So that turns out to be okay, but there's faster ways to go if you know something about your data. So you'll notice that we first insert Kim, Jane, and Kay, and then we're going to go ahead and we're going to insert a couple of other fields that are kind of at the end of this. And so what we can do is we can use the end iterator to give us the end iterator in the tree, and then we can go ahead and insert Kurt and Mike. And of course, Kurt and Mike have values, have keys that are after the ones we've already put in the map. And by giving it the end iterator here, that will help it be more efficient in terms of how it puts that item into the map in the right place. So it doesn't actually have to do a binary search from the top down to the place where it goes. It just goes ahead and sticks it at the end and rebalances the tree. And that'll be a little bit faster, probably more like sort of constant time as opposed to log n time. You'll notice that this is just a hint, however. So if we try to put Kim in here, Kim is probably not going to work with that because it's not really at the end. And so as a result, that'll have to start from the top and go down. The next thing we're going to do is we're going to define a vector of value type. So this will be a vector of these string-to-string pairs. And we're going to call this the McKay's names vector. So you can see we have Sophie McKay, Steve McKay, and Kim McKay. And then we're going to go ahead and insert from the beginning of that vector to up to, but not including the end. So this is allowing us to be able to do an insert of a range of values. And so we're just using the vector here to do that. We probably could have done this with inlining and not had to make a special vector, but I wanted to keep it clean and clear what was going on. So that's a nice kind of little optimization, so you don't have to write everything out. This would make more sense if we had a lot of elements that we were trying to do here that we perhaps already had in a vector, for example. So now what we're going to do is we're going to go ahead and print all the names. And notice when we do this call here, this names call with the insertion operator, that's just going to go and call this version here. That's going to call this insertion operator to print out the contents of the multimap. So see how clean and consistent that is relative to other uses of C++ and IO streams. We then come down here and we say, please find me a pair of iterators that contain all of the keys that have the word Kim in them, or the name Kim in them, the first name Kim. So what we're going to get back here is a pair that's going to have iterators to the beginning of the first Kim to the end Kim. And that's a nice, convenient way of finding all the Kims, because it's a multi-map, so we can get all the elements together. We then go ahead and print out the number of people called Kim, and then we go ahead and print out the people called Kim. So it's going to print out all the people whose names start with Kim. Then what we're going to do is we're going to go ahead and erase everybody whose name starts with Kim. And we can do that by just giving it that pair first and pair second. For some reason, you can't just give it a pair. You have to give it an iterator range. So we go ahead and erase everybody called Kim. Then we print the updated map that has erased those people. And then the last thing we do is we go look for someone named Kurt. If we don't find Kurt, we say Kurt's not found. But of course, we have a Kurt, because we put a Kurt in somewhere up here, Kurt Jones. And so when we're done, we go ahead and print out Kurt's last name is iterator arrow second, which will be his last name. So let's go ahead and run this code, see what we get. And lo and behold, we start out by printing everybody. So it says Jane and Kay and Kim belong to the Smith family, and then Kim belongs to the Jones family. And you can see we've got different people in different places in the map. And then you can see that we print out all the people named Kim from the different families. Then we removed all the Kims. Then we printed the results where we don't have any Kims left. And the last thing we do is we print out Kurt's last name is Jones. So I like this example. I think example is really cool. And it demonstrates lots of other cool features and powerful features of multi-maps in STL. So the next thing I want to do is I want to keep with this example, but I want to do a little bit of optimization to it and show you what the consequence of this optimization is going to be. So we're going to keep pretty much everything the same. We're going to have the same data types and so on, and the same helper functor and the same helper insertion operations and so on. But the main difference here is we're going to go ahead and we're going to demonstrate the difference between inserting and emplacing. So over here, you can see that we're inserting value types here, and we'll take a look at the consequences of this. And then we're going to do emplacing instead of inserting, and then we're going to do something called emplace hint, which is like that insert that used the iterator as a hint. And then we're just going to go ahead and print the names out. I didn't want to redo all the code, but it would all be the same. To make this interesting to look at, we're going to replace the use of string with our simple string. So if you recall, simple string is this little class that I wrote that shows off a bunch of interesting STL and C++ capabilities, particularly related to the rule of 5, where you need to have all the different methods and constructors and move assignment operators and destructors and so on provided. So let's go ahead and run this code, and you'll get a chance to see the reason why emplace is such a win relative to using insert. And it's really quite startling when you look at the code. So this is what happens when we insert those elements into the map. Now keep in mind, just to be clear here, you can see the lines of code. So here's the code. We do insert for 3 value types. And look at all the stuff that takes place just to do that. So you can see that we're calling the simple string constructor that converts a const char star into a simple string. Then we're calling the copy constructor. Then the move constructor is being called. Then a bunch of destructors are being called. And that's basically for every one of the things we're creating here. All this work is being done. Wow. Very expensive because of the value semantics of C++. Well, of course, there's got to be a better way, and in fact, there is. And so look how much better it is to use emplace. So you can see emplace is just going to basically emplace the char stars into the multi-map just by simply calling the simple string constructor that takes a const char star and creates a simple string. So I think you'll agree with me that that is way, way, way more efficient, way more concise than doing all the gobbledygook with insert. So I think the rule here, much like with insert back for vectors and other containers, using emplace instead of insert is usually a win. And it's also interesting to take a look at the code for both these things. Let's go take a look at insert. You can see what it does. So insert in this case is going to be this move constructor version, but it's still got to do some work to create those things and copy them and so on. Conversely, when we go ahead and take a look at emplace, you can see what emplace does is it uses the variadic template features in C++ to just go ahead and take the arguments that are passed in, those 2 strings, and just copy them in place or move them in place into their final destination. So it's way, way, way more concise. And then we also have emplace hint, which is very much like the insert method for map, where you can give it an iterator. And if you play your cards right, that'll use the emplace logic, as you can see here, and it'll also put it into the map without having to search from the top each time, if the hint is set up to do that kind of thing. You might wonder why we have to have a method called emplace hint, as opposed to having a method like we do with map, where insert is simply overloaded. And the reason is because we otherwise would not be able to differentiate between the var args that are passed in to emplace. You can see here's the emplace version with a bunch of var args. This one we have to explicitly call out the iterator as the first thing, otherwise it would get lost in the var args that are passed in. So they had to use a slightly different name, but I think it's still pretty cool and pretty obvious what's going on. Okay, so that was the example showing how to use some other features in multimap, in particular how to use emplace, and a big win. So I recommend you use emplace instead of using insert. All right, we got one more example here, and this will be kind of fun. Let's go over here and open up 5.7a. So thus far, we've been talking exclusively about ordered associative containers, which are implemented under the hood with the red-black trees, as we've talked about. What we're going to do now is just show an example of an unordered associative container. And I won't show you more than just this one example, because all the unordered associative containers basically mimic the API of the ordered ones, with the difference being that they're not ordered. So instead of being ordered using a red-black tree as the ordered ones are, all the unordered associative containers use hashing and hash functions. So let's take a quick look at this, and it generalizes quite nicely. So there's a parallel set of unordered associative containers that are all prefixed with the unordered underscore prefix, and the ordered containers don't have that prefix. I think if they'd done STL from scratch at this point, they probably would have called the other ones ordered underscore map, ordered underscore set, but those already had their names long ago, and the unordered ones came in with C++ 11. So the main difference, of course, is it doesn't use a binary tree, so it doesn't need the less than operation. Instead, here the parameters are passed. So we have the key type and the value type, just like for the ordered associative containers for things like map and set, well, at least for map and multimap. And then we have some other things that weren't in the ordered containers. Remember, the ordered containers all took the compare functor, which was defaulting to less. And for the hash table implementation, for the unordered version, you pass in a hash function or hash functor, which defaults to the standard hash functor, which is then specialized for all kinds of different types. Or you can define your own if you need to. And then we also have a predicate functor, which is used if two keys hash to the same location in the hash table. Then the predicate is used to be able to do comparisons when they do the collision resolution process, which just basically searches down a linked list until we find something that matches by equal to. And then the allocator is the allocator as always. So the main difference between ordered maps and unordered maps is they just don't store them in an order. That's really the only difference. Otherwise, they're all the same semantic. Okay, so let's go ahead and take a look at an example. What we did is we took our example from before, the one that's now is the time for all good people to come to the aid of their party example. And we're just going to replace the use of a map with an unordered map. That seems pretty simple. And in fact, it is pretty simple. The rest of the code starts out pretty much identical. We iterate through the word list and throw the elements into the map. The difference now, of course, being that the map uses hashing, not less than, in order to be able to store the item in the map, in the unordered map, in the appropriate place in the hash table. I'm assuming everybody here knows what a hash table is. That's a topic that's typically covered in an introductory course on data structures or algorithms. So I hope you know what that is. Basically, it's a way of taking the values in the key and then computing a function that maps them into a table. And then if there are things that map to the same location, they're resolved by having a linked list of things that hash to the same location, using that equal to function to figure out if they're the same value or not. Keep in mind with a map, you can't have an unordered map, as we're showing here, cannot have duplicates, whereas of course an unordered multimap could have duplicates. Now, just for kicks, we're then going to go ahead and print the contents of the unordered map out. And you'll see when I do this, they're not ordered in any particular way. They're just however they happen to hash. Then what we're going to do is we're going to go ahead and create a vector of pairs. And we're going to go ahead and we're going to push the elements into the vector. So we're going to take each element in the word map and we're going to put it at the end of the vector. So it's going to do emplace back, to be efficient, of course. So now we're going to have a vector of all the contents. And then we can go ahead and sort those contents. So we're going to end up with a sorted version here, but that's going to be after we've put it into the unordered map. Now, if you really want it to be sorted, use an ordered map. But this is just showing how you could take something that was unordered, and then you could go ahead and put it into a container and then sort it. And we're going to sort it using the greater functor, so it'll be in descending order when we print it out. You also could have used this code here instead of using the for loop with emplace back. And it turns out that there's actually a clever back inserter that is used here. And if you take a look under the hood, they have a version of the back inserter that both uses the, I think they have one here that uses the reference values and move semantics, and others that use other semantics. But notice that that's doing basically a pushback here. And so if you take a look here, you can see that we have one that uses a const ref, and then the other one that uses basically the R value references. And this uses move semantics. So that should be a little faster, but it's probably fastest to use in place back is my guess. I haven't really sat down and benchmarked these things, but this might be a good case where sticking with the for loop, the range-based for loop might be the way to go. Okay, when we're all done, we're going to go ahead and print things out, and then we're going to total everything up as before using our lambda function. So that's pretty much what we had done earlier. Let's go ahead and run this code, and it'll show you a couple of interesting things. As you can see here, when we first print the results, they're not ordered in any particular way. So that just happened to be the way that they hashed into the hash table. So no particular ordering. They're not ordered in alphabetical order for sure. Down here, after we stuck them into the vector and then sorted them in descending order, when we print these out, you can see that they're now sorted in descending order. And as we saw before, the number of words is 16. We used the lambda for that. So those are the things that I had wanted to talk today about. These are giving you hopefully a very good understanding of how STL maps and multimaps that are ordered associative containers work, as well as also getting a chance to see how at least one of the unordered associative containers work, which in this case was map. And if you take a careful look at this, I think you'll really learn a lot. I highly recommend you take a look at the source code. As always, feel free to clone my repo. Feel free to play around with it, do what you'd like with it. It's all open source, so whatever you want to do, it's up to you. And if you enjoyed this content, please go ahead and like and subscribe. And of course, you can feel free to follow me on Twitter so you can get notifications when my videos will be going up and the sessions I'll be recording are going to be broadcast. So thanks very much, and I will look forward to talking to you soon.